A typewriter looks simple because its purpose is simple. Press a key and leave a clean letter on paper. But a useful office machine had to repeat that trick thousands of times a day, with speed, alignment, readable impressions, and almost no tolerance for failure. The basic problem was mechanical translation. A finger moved only a short distance, yet the machine had to choose one character, ink it, strike it at exactly the right place, tray the paper by one space, and reset itself before the next finger arrived. Early designers could solve any one of those jobs elegantly. Combining all of them created a nest of levers, springs, linkages, and compromises. Faster typing increased the risk of collisions. Better print quality often added mass. More characters usually meant more complexity. Chalk typing also changed the scale of writing. A letter no longer had to carry one clerk's handwriting. It could become standardized, copied with carbon paper, filed, and read by strangers across a company or a government department. So this is not a beauty contest for antique machines. The field is general-purpose office typewriters before electronic word processing, judged by typing control, print quality, adaptability, reliability, practical scale, and influence on what came after. A contender must do more than introduce one clever feature. It must make sustained writing measurably better for ordinary users, survive the punishment of real offices, and leave a design logic that competitors or later technologies could not ignore. That standard is severe because the typewriter's history is full of brilliant machines that solved the wrong bottleneck, enhived before supporting systems existed, or required users to abandon habits that had already become infrastructure. The Scholes and Glidden typewriter proved that mechanical writing could become a commercial product rather than a perpetual inventor's demonstration. Manufactured by Remington and sold from the 1870s, it helped establish the cylindrical platen and the keyboard arrangement that evolved into QWERTY. Its achievement was not polished convenience. The first model printed only capital letters, and its type bars struck the underside of the platen, so the operator could not immediately see the line being written. Even the name typewriter still sounded like an explanation. Yet it established the commercial grammar of the field. One key for each character, a moving carriage, a ribbon, and trained touch typing. Later machines would spend decades repairing its weaknesses while preserving much of its interface. James Hammond attacked a problem from a different direction. His machines used a curved type shuttle instead of a basket of individual type bars. A hammer pushed the paper against the selected character, producing remarkably even impressions. The shuttle was interchangeable. Different scripts, symbols, and type styles could be fitted without rebuilding the machine, and the multiplex could hold 2 shuttles ready for use. Its slogan, "For all nations and tongues," was unusually literal advertising. That adaptability made the Hammond valuable for specialized writing, but its operating feel and mechanism stood apart from the emerging office standard. It remained a successful alternative rather than the architecture around which the mass market organized itself. George Blickensderfer pursued lightness and economy. His number 5 used a compact type wheel and far fewer parts than a conventional standard machine. It was genuinely portable at a time when many office typewriters were furniture with a keyboard attached. He also challenged QWERTY with the diatatophon layout, placing frequently used letters where he believed they could be reached more efficiently. Boyers could order QWERTY, but the alternative showed how little of the familiar keyboard was mechanically inevitable. The machine was clever, compact, and internationally sold. Its problem was strategic. Portability could not outweigh a non-standard keyboard, a different typing action, and the growing value of training people on machines that behaved alike from one office to another. The strongest mechanical rival emerged when visible writing became non-negotiable. The Underwood Model 5 placed the type bars so they struck the front of the platen. Typists could see the line as it appeared, instead of lifting the carriage or trusting blind work. Introduced around the turn of the 20th century, it gathered the modern standard into one durable machine. 4 keyboard rows, front strike, a shift mechanism, rude spools, and an open type basket that could be inspected and serviced. The design became so influential that its outline is almost the dictionary picture of a typewriter. It spread through offices, schools, newsrooms, and public institutions, while competitors copied the visible writing arrangement that users quickly came to expect. Its virtues were conservative in the best engineering sense. The machine was understandable, repairable, fast in skilled hands, and built around a mature supply of ribbons, training, desks, and service. It did not need the world to reorganize itself. But the Model 5 also perfected the architecture that imposed the field's old ceiling. Every character still needed its own swinging bar. Rapid adjacent strokes could clash, fonts were effectively fixed, and the heavy carriage had to shuttle the paper back and forth for every line. The IBM Selectric is the GOAT of the office typewriter age. Introduced in 1961, it did not merely improve the standard machine. It removed the type bar basket and the moving carriage that had defined office typing for generations. In their place was a small spherical type element carrying 88 characters. When a key was pressed, the element tilted and rotated to present the correct letter, struck the ribbon and paper, then moved sideways to the next position, while the sheet itself stayed still. That motion looked playful, but the selection system was serious mechanical computation. Nets of links and differential mechanisms converted each key into a combination of tilt and rotation. The machine was in effect decoding a physical command before printing it. Because there were no converging type bars, the familiar high-speed jam disappeared. Because the printing element traveled instead of the carriage, the paper did not lurch across the desk after every character. A typist received a lighter, more controlled action without sacrificing a hard copy. The element could also be removed in seconds. One machine could switch among typefaces, leans, mathematical symbols, and specialized alphabets by changing a component small enough to hold in one hand. Adaptability stopped being a specialist machine trick. IBM had to redesign the letters themselves because the element did not hit exactly like a traditional bar. Serifs and character shapes were adjusted, so impressions looked even. That attention mattered. Office machinery was now expected to produce typography, not merely legible marks. The elegance visible to the user concealed formidable complexity. A Selectric contained roughly 2,800 parts. Its victory depended on precision manufacturing and a service organization capable of keeping those parts adjusted in thousands of ordinary workplaces. This is where the comparison with the Underwood becomes decisive. The Underwood was the stronger answer to the 19th century typewriter, durable, visible, standardized, and mechanically intelligible. The Selectric changed which problems an office typewriter was allowed to solve. It was not a laboratory curiosity. IBM sold about 80,000 units in the first year, 4 times its projection, and more than 13 million across the product line. By 1978, IBM held nearly all of the electric typewriter market. Public demonstrations made the difference tangible. At the 1964 New York World's Fair, visitors used Selectrics to type postcards and felt how a light touch could command a complicated machine. The future arrived as a better keyboard before it arrived as a screen. The architecture then escaped the category. IBM paired the mechanism with magnetic tape so text could be stored, revised, and printed again. The magnetic tape Selectric typewriter became an early word processing system, turning typing from a one-pass act into editable information. Fen Selectric mechanisms also became computer terminals. The IBM 2741 let users type to remote systems and receive printed responses. A special element helped make the symbol rich, APL programming language practical at the terminal. That adaptability even had a darker consequence. During Project Gunman, investigators found Soviet listening devices hidden inside Selectric typewriters used at the United States Embassy in Moscow. The machine's precise internal motion could be observed because it encoded each character mechanically. The Selectric was not universally superior. It needed electricity, cost more than many manual machines, and demanded skilled maintenance. Its complexity could turn a small fault into a service call, while a competent mechanic could understand much of an Underwood at a glance. Nor did it defeat the computer. Electronic word processors and inexpensive printers eventually made the entire contest obsolete, and IBM retired the line in 1986. But obsolescence is not the same as defeat when a machine helps create its own successor. The Selectric earns the title because it combined speed, quality, interchangeable character systems, mass adoption, and a direct path into word processing and interactive computing. Its GOAT status matters because it shows the highest form of a mature technology, not perfecting the old limit, but making the next medium possible.